Okay, this is section 1.2. We're going to be talking about function notation here. As you know, the graph of a function gives the ordered pairs x comma f of x, which together make up all of the points that are defined for that function. When we talk about the value of a function, that's the distance y from the point x, right? So if I pick a point x here, right, the y value is this, right? Well, that distance, that's y, or f of x. Okay, so that's what we call the value. So it's basically the distance between the x-axis to the graph. All right. So let's take a look at this example here. We have the graph of this function f of x, which is a quadratic function, so it gives us a parabola. And what we want to do is first we want to find f of 1, then f of 3.5 from the graph, and then confirm algebraically. So if I do f of 1, 1 is the x value, I go to x equals 1, and if I move up to where the graph is, that's at y equals 1. So I say f of 1 is equal to 1. So that's graphically. Now, if I wanted to do it algebraically, I would say f of 1 is equal to, and I would plug that value 1 into the function. So I would say 1 squared minus 4 times 1 plus 4, and that is 1. Okay, so next, if I wanted to find f of 3.5, 1, 2, 3.5 is here. And if I were to follow that graph up here, it's somewhere around here. So I would say it's about 3. Okay, and same thing. If I were to plug it into the function, I would get the value algebraically. All right, let's talk about domain and range. The domain of a function is all of the x values for which a graph exists. All right, so take a look at this first one here. If I start looking along the x-axis, starting from the far left, right? And if I close in here, where is the first point where I hit a graph? Well, here at -4, right? And then I have a graph for all of the x-axis, for all of the x values until +4. So I say my domain starts at -4 and ends at +4. So I'm going to say it goes from -4 to 4. And because I have open circles at -4 and 4, I put open parentheses here. So at x equals 4, there is no graph. But at 3.99999, there is a graph. Range is the y values. Okay, and again, if I started from the left here, from the negative values, then I start from the bottom here, and I just scan the y-axis upwards, and I see for which y values there is a graph. Here, notice the first time I hit a graph is at y equals -4, and it goes up to y equals 0. So I say it extends from y equals -4 to 0. I have a graph at -4, but open circles at 0, so that's how I write it. Okay. This next one is a continuous graph, and it's assumed that it extends downward here and upward there, and it's also slowly inching its way towards the right and the left. So the domain is all real numbers. This graph exists for all real numbers from -infinity to +infinity. The range, same thing, extends for all y values from negative to +infinity. Okay. Here, quickly, this extends to the left and right and upwards. So for the domain, I have a graph for all x values except here there is an open circle at 2. So I have a graph from -infinity to 2 and from 2 to infinity. Y values, right? If I start scanning bottom up, the first time I hit a graph is at y equals 1. So this goes from 1 to infinity. Okay, now take a look at this one. Here, I have an endpoint, an actual endpoint. That means the graph ends there. It doesn't extend past that. So if I'm looking at the x values, the graph definitely starts at -8. And then if you see here, it continues. Now here, that one leaves off, but another one picks up. So technically there is a graph there as well, and it extends continuously until x equals 6. So the domain there is that. Now the y values go from 0 to 8, open at 8, closed at 0. Okay, let's talk about intercepts. Intercepts are where the graph hits the x or the y-axis. All right, it's more straightforward to talk about the y-intercept. Let's start talking about that one. The y-intercept is the point where the graph intercepts or hits the y-axis. To find the y-intercept, we find f of 0. So just plug 0 into all of the x's. Okay. Now, x-intercepts. X-intercepts are where the graph hits the x-axis. The x-intercepts of the graph are also called the zeros. They are called the roots of the equation. Okay, and they are also called the solutions. So all of those 4 are synonymous. To find the zeros of a function, you set the function equal to 0. So for example, if the function is x squared plus 7, you set x squared plus 7 equal to 0. All right. Now, let's take a look at this function and let's find first the y-intercept and then the zeros. Okay. I'm going to do it algebraically first. So for the y-intercept, you want to find f of 0, which means you plug 0 into each of the x's. And so that's going to be 0 cubed minus 0. So we say f of 0 equals 0. And you know what? That's how I want you to write it. F of 0 equals 0. Okay? All right, so how about the zeros? The zeros are where it hits the x-axis. So we're going to take f of x and set it equal to 0. Do you see how it's a different concept? This means if f of x is x cubed minus x, that's what I set to 0. Factor out an x, I get x squared minus 1. Factor some more, x minus 1, x plus 1 equal to 0. So here, x is 0, x is 1, x is -1, okay? And the way I want us to write the zeros is in function notation. So we're going to say f of 0 equals 0, f of 1 equals 0, f of -1 equals 0. So that's telling us at those x values, 0, 1, -1, the y value is 0. Okay? All right, let's move on here and let's look at symmetry. All right, let's test these functions for symmetry. Okay, a function can be symmetric along the x-axis, the y-axis, or the origin. Let's take each of those separately. If a function is symmetric with respect to the x-axis, then you see in the diagram to the right how it looks, right? It's basically you could fold over the graph along the x-axis and the upper and the bottom parts will match. Okay, how do we test for symmetry? You have to substitute -y for y and simplify. If the result is the same as the original, it's symmetric around the x-axis. Okay, how about the y-axis? If a graph is symmetric around the y-axis, this is how it looks. If I fold around the y-axis, left and right parts match perfectly. To test for symmetry, you substitute negative x for x and simplify. And then if you get the same as the original function, it's symmetric. Okay, to check if a function is symmetric with respect to the origin, the graph on the right is how that looks, right? So basically, imagine folding the graph over vertically and then again horizontally, and then those parts will match. And to test for that symmetry, substitute negative y and negative x for x and then simplify. If none of these work, then the function has no symmetry. Okay, let's do a couple where we just look, graphically. Take a look at A. Does that have symmetry? Well, yeah, it looks like it's symmetric around the x-axis. So I say this has x-axis symmetry. B, it's symmetric around the y-axis. C, it's symmetric around the origin. D is just symmetric around the y-axis. Okay, no other way of basically folding that will get your, different parts to match. Okay, now how do we do it algebraically? How do we test for symmetry algebraically? What you have to do is basically divide your paper into 3 parts. And you want to test first along the x-axis, the y-axis, and then the origin. Okay, for the x-axis, you want to substitute negative y for y. So you start with the function, right? For y, you want to replace y with negative y. And then you have to simplify this function. So solve it for y again. When I solve this for y, what do I get? Y equals negative x cubed. Now, did I get the original function back? No, this is different from the original function. So it's not symmetric against the y-axis. I'm sorry, the x-axis. Now let's do y-axis. I start with the same function. This time, you're going to replace x with negative x cubed. So I get y equals negative x cubed when I simplify. Did I get the original function back? No, it's not symmetric with respect to the y-axis. Now let's do origin. Y equals x cubed is what we start with. I'm going to replace y with negative y and x with negative x, and then simplify. Negative y equals negative x cubed. The y's go away. I get y equals x cubed. Did I get the original function back? I did. So I say this is symmetric with respect to the origin. Right? Okay. Now, let's talk about even and odd functions. Okay, let's talk about even and odd functions. Functions that are symmetric with respect to the y-axis are called even functions. Functions that are symmetric with respect to the origin are called odd functions. Okay. How do we determine? Here's what you do. You substitute negative x for x, okay, and you find basically f of negative x. So for this one, you always start out with the same thing. You always just find f of negative x. If you get the same function back, then the function is even. But if you get the negative of the function, then the function is odd. So for it to be an odd function, every term should switch signs. That's when it's an odd function. All right, so let's take a look here. So for even and odd, we're always going to just find f of negative x. Let's find f of negative x. We're going to plug in negative x for each of the x's. I'll rephrase that. Replace every x with negative x. Okay, that's all I'm doing. Take out x, put in negative x. Now, let's simplify. Here I get x squared. Here I get plus 4x plus 4. Okay, now, compare with this function. Is it the same? No. Did every single term change signs? No, only one of them changed signs. So this is neither. All right, take a look at this next one. F of negative x is negative x squared minus 4. Simplify that, and you get x squared minus 4. Compare with the first one. We got the same function. It's even. Here we go. F of negative x squared over negative x to the 4 plus 1. What does that give me? X squared over x to the 4 plus 1. Same function. Even. Okay, how about here? F of negative x is 1 over negative x, which means it's negative 1 over x. So take a look. This term changed signs. Everything changed signs. So this is odd. Not odd in a bad way, just, odd versus even. Okay, here, f of negative x is negative x squared minus 3. X squared minus 3, same as before, even. Okay, I'm just going to add one more here, just to make it symmetric. Haha, get it? All right, let's do f of x is equal to x cubed plus 5x, right? Okay, f of negative x is negative x cubed plus 5 times negative x. That's negative x cubed minus 5x. Look at what happened. This term changed signs. This term changed signs. Because every single term changed signs, we say it is an odd function. Okay? And with that, I will let you go and take care of homework. Thank you.